Hey guys, on to 8.7. I'm sure you noticed we're jumping around a lot in this unit. So this is covering applications of derivatives, so how they apply to other problems. Today we're going to look at L'Hopital's rule. You guys are going to absolutely love this. It makes life so much easier. Let's go back to the beginning of school. Do you guys remember this indeterminate form, 0 over 0? And we also have infinity over infinity. And this meant direct sub really was no help to us. And we had three algebra things that we used. Try to remember what they are. So we factored, we rationalized the numerator. And really rationalizing is fine, but a lot of times it was the numerator. And then we had fractions, so we had to get common denominators. We also probably called it like combined like terms. Okay, so all of these methods, they worked, we were good, but now there's a different way that is so awesome and helpful. Okay, so let's look at this first problem. So let's make a guess as to what we think the limit will be and then check by evaluating on your calculator. So when we go to do this, if you sub a 0 in, here, e to the 0 is 1, 1 minus 1 is 0, so we get 0 over 0. So there's that indeterminate form again, which really doesn't help us. It just means do something else. Well, look at your choices above. Factor, rationalizing, common, nothing there. Do you guys remember your sine and cosine, those special trig limits? Those aren't helpful. Okay, so what can we do? Let's try graphing using our table. So let's use our table. Let's go 1, 2, 3, 4, 5 in, 2, 3, 4, 5, and we know that at 0 we get d and e because look at, you can't sub a 0 in the denominator, right? That's a no-go. So let's start, remember we're going to creep in, so we're going to go, let's start at negative 0.1 and 0.1, and then we'll come a little closer. So 1/10, let's do negative 100th, 1,000ths, and now let's just get carried away and write 5 zeros. 2, 3, 4, 5. Starting over here, we're 1/10 away. Then we're going to get 1/100th, so we're creeping up on this, and now let's 2, 3, 4, 5. We're getting really close. Okay, pull your calculator up. Let's go to alpha y equals. Remember, I love that fraction tool, but how about we put it in y equals first? Okay, so let's go to alpha y equals, hit enter, now we're here. The numerator is e to the 3x. Go ahead and type that in. Minus 1. And then in the denominator, we have just an x. Okay, if we just graph on the standard window, we get this function. So we are approaching 0. At 0, actually it shows a break if you look closely. At 0, we know the function doesn't exist. If you guys look at this, can you see that the limit is coming in from the left and the right, and it looks like it's matching up? Sorry, let's go back here. Okay, so like over here at 0, it looks like there should be a 3 there. Let's see if the table can help us out, or let's just fill these numbers in actually. So remember, if you hit trace and you type your number in, so negative 0.1, we'll get our answer of 2.592. I'm going to let you guys do this on your own, and we'll go back to the table. So go ahead and type these in. Remember, trace, and then just type your number in, negative 0.01 for the next one, and you get 2.955. Okay, I'll see you back there. Okay, so here's what you should have gotten. Look, 2.59, 2.95, 2.99, and then 3. Clearly from the left, it looks like we're approaching 3. From the right, 3.5 about, 3.0, 3.00, yep, closer to 3. So it's not just that these are the same, it's that the numbers building up also lead there. So I'm pretty confident now that our answer is 3. We saw it on the table, we saw it on the graph, we're good to go. Okay, so I want you to know on this problem, we had no other way to solve it other than to use our calculator. Okay, we still have not gotten to the good stuff yet. Okay, going down. We'll get to those guys in a sec. Let's look at these problems. So these problems involve some earlier like algebra things that we did. So on this first one, what are you thinking? You sub a 0 in. You guys should get 0 over 0. It's indeterminate, more work. I hope you're thinking to factor. This is screaming for you to factor. If you take a 2 out, you have x squared minus 1, which is x plus 1, x minus 1. Look at this bottom piece is the trouble, because if I sub a negative 1 in there, I get 0 over 0. Remember, we always try direct sub first. Those cancel, so everything's working out like we would expect. Now at this point, guys, remember we're writing limit every single time. We get here, now is direct sub legal? It sure is. So now you're going to get, what is this? If we sub a -1 in here, -1 minus 1 is -2, and -2 times 2 is good old -4. Okay, we're awesome at those. On the next one, so this was from, I believe, 3.5 when we were looking as x goes to infinity. Hey, as a reminder, remember as x goes to infinity, that's a horizontal asymptote. To find horizontal asymptotes, you want to see when x goes to positive and negative infinity. Now, we're not even going to do any work on this one because we notice that these are the same exponent, ratio of leading coefficients, 3/2. Remember, the long way is to divide everything by the degree in the bottom, and you would have got the same answer. So that's just ratio of leading coefficients. Going on, if you sub a 0 or sub a 7 in here, you get 0/0, which again is indeterminate. I hope you're realizing here to rationalize. Okay, so we write limit every time. You FOIL, first times first is x plus 2, outside, inside cancel, the last is -9. Denominator, we have this whole thing, x minus 7, square root of x plus 2 plus 3. Remember your plan. Oh, this is a 7, it just looks kind of messy. This guy is the trouble. Okay, so we need an x minus 7 up top. If you look at it, you see that you have that. Again, now we feel a little better. Everything is working out beautifully. Those cancel. Now you can go ahead and write the final one. X plus 2 plus 3. Notice limit every single time, guys. The equal sign's over here. We're taking limit of the function. Replace 7. Replace x with 7. Now we're good. This gives us a square root of 9, which is 3. And 3 plus 3 is 6. So we are left with 1/6. Okay, going on to this little story now. So look at these two guys. One's Bernoulli and one is L'Hopital. So L'Hopital was the title of the notes. What happened here, and there's a little backstory, we'll talk about it more in class, but if you read on, you'll see that the mathematician Bernoulli discovered this rule, but it's actually called L'Hopital. So doesn't that seem a little sneaky? Who do you think, from the looks on their faces, L'Hopital and Bernoulli? Okay, we'll talk about that in class and see if you guys can figure it out. So what they're claiming is Bernoulli discovered it, but L'Hopital really published it. So a little drama in the math world. We'll talk about that in class. Okay, going on. L'Hopital's rule, or this is just meant to recap the story, or Bernoulli's rule as it was. So look what's happening. As x goes to a of f over g, and if you get 0/0 or infinity over infinity, then what you're allowed to do is take the original limit and take the derivative of the numerator, take the derivative of the denominator, and you end up with the same thing. Now, you'll realize shortly why this is so cool. So if we have a limit problem that we don't love, right, and we get 0 and 0, infinity over infinity, and it has all this work, well, what they're saying is, hey, how about you just take the derivative of each one, see if it works out better for you. Okay, so that's what we're going to try. I tried matching up these ones that we did by hand over here. So look at this first one. This one is actually this problem. Now I'm asking you to go ahead and let's use L'Hopital's rule. So if we use direct sub, we get 0/0. That was the condition. I'll try to leave this up. You needed 0, 0, infinity over infinity. Now that's code for you. Go ahead and use L'Hopital's rule. So instead of having to factor and cancel, and we saw in chapter 1, that could get kind of messy. If you take if f turns into f prime, take this derivative. Isn't that just 4x? What's the derivative of the bottom? What's the derivative of x plus 1? That's just 1. So what happened was before you couldn't sub the -1 in because you would get a 0 in the bottom. However, now our issue is gone. Without factoring, without anything, sub -1 in here and you get -4 and we're done. Pretty cool, kiddos. Okay, so this was the same as 2a. We got the same answer as 2a, but now we don't need to factor. Remember this guy? We just looked at this one right here on C, and look at all this work we had to do. Okay, now though, when we use direct sub, remember we already said that we got 0/0. So now we can use L'Hopital's. Hey, one thing to point out, I get these two are divided. You are not using quotient rule. It's saying f turns into f prime and g turns into g prime. Okay, so limit as x goes to 7. Now remember this x plus 2 is really to the half. So you bring the half down, you have x plus 2 to the negative half, and you guys don't forget the inside stuff. What's the derivative of this? Chain rule, that's just 1, so we're okay. Now look at the bottom used to give us a 0. Now when I take its derivative, I get a 1. So my problem is gone. I did not have to rationalize. So now I have 1 over, the 2 goes in the bottom, the square root of x plus 2 goes in the bottom, and that 1 in the bottom is completely irrelevant. Now I'm allowed to use direct sub. If you look over here, if you sub a 7 in, you're going to get the square root of 9, which is 3. 3 times 2 is 6, and we're done. Okay, this was the same as 2c. Sorry, that's writing so weird. Okay, going on to this next one. Do you guys remember c? C was up here, and we really had no other option other than to make this table. All of our awesome techniques did not work. So now let's see if good old L'Hopital, or Bernoulli, as you will, if you will, can help us out. Go ahead and sub a 0 in, you get 0 over 0. That means L'Hopital is good to go. So we learned this derivative. Remember, it was one of our favorites. All it says is to copy it over, multiply by the derivative of the exponent. When we go over here, the derivative of 1 is none. Oops, where'd we go? And then the bottom now, what's the derivative of x? 1. I want you to notice the pattern here. Before subbing an x in, subbing the 0 in gave us a 0 on the bottom. Once we take its derivative, we no longer have that issue. Now direct sub is okay. We're going to have e to the 0 times 3, and really you could have just went to 3. Okay, and this is the same as 1a. If you go back and check, all these answers are the same. Okay, we're not going to do one like that again. This is a like all the ones that we saw previously. This is a completely new one. You guys remember, you have to memorize this natural log graph. It's going to help you a lot this year. That's the ordered pair 1, 0. So as x goes to infinity, guys, doesn't this also go up and up and up forever, even though it's slow? And you guys know the square root function. The square root function does this. That also goes up and up forever. The question is, who's going faster? Is it top heavy, bottom heavy? Like, we don't have a polynomial to compare, so we're out of options. Remember, as we go to infinity, that's a horizontal asymptote. L'Hopital said not only 0 over 0, also infinity over infinity. So let's go ahead and L'Hopital this. What is the derivative of natural log of x? It's 1 over x. In the denominator, we have a 2. That x is really to the half. So you bring the half down, decrease the power. Okay, if we copy this over, just because it looks absolutely terrible, we're going to have 1 over x over, now look on the bottom, these cancel, and you're left with, this becomes, let's see, this becomes 1 over root x. Because we're dividing by that, you can multiply by its reciprocal. So I'm going to get root x over x, and isn't that really 1 over root x? Now, remember this idea, if the bottom gets big, 1 over a big is 0. Okay, so much less work. L'Hopital, now that we know it, we can use it. And then you guys will say, well, why didn't you teach us back in chapter 1? Well, remember back in chapter 1, you didn't know derivatives. So how would you be able to take this derivative? Okay, but now you know so much and we can use it. Okay, on the next one. Well, what does this mean? We have to repeat ourselves and then we say it twice? Let's see what this is talking about. So let's go ahead and hopefully that's a typo, right? We don't want to do things twice. If you sub a negative infinity squared, now, right, this isn't like totally legal. You can't really work with infinity. We're just kind of thinking about it. As you sub a negative infinity squared and you get infinity. Now on the bottom, you have a negative here, but I'm subbing in a negative infinity. So it becomes e to the positive infinity, which is also infinity. That's our ticket to use L'Hopital. Let's go ahead and do it. So we are going to use L'Hopital. So we have the limit as x goes to negative infinity. Remember, guys, horizontal asymptote, if it goes to positive or negative infinity. Take the derivative of the top and you get 2x. The derivative of the bottom, copy it over and take the derivative of the exponent. Now, if you look back above, look at how much nicer the problems got every time. 1 in the bottom, 1 in the bottom, 1 in the bottom. Not 1 in the bottom, but we're able to work with it. this, we still have x's everywhere. Let's go ahead and see what happens. Go ahead and sub in a negative infinity. So in the numerator, we're going to get 2 times negative infinity, which is negative infinity. On the bottom, we have a negative here, so we're going to have a negative. Then, if you sub a negative infinity in here, the negatives cancel and you get infinity. And what's e to the infinity? Shoot. So up above, every time we did this, we got an answer. We L'Hopitaled it, got an answer. L'Hopitaled it, got an answer. L'Hopitaled it, not so much. But what's up with negative infinity over negative infinity? That's our ticket to use L'Hopital. So that wasn't a typo. We do have to repeat ourselves. So now let's go on. Derivative of the top, the numerator, which is 2. The derivative of the bottom, copy it over, and then take the derivative of the exponent. That's a -1 times a -1 is here. Now, even though the bottom didn't get prettier, didn't the top? Now we just have a 2 instead of an x. Now remember this next thing, we can't really work with infinity, so this is just like our thought. If you replace x, so we have negative, but then we replace x with a negative infinity, now we have 2 over e to the infinity. What's 2 over a huge number? That is a 0. L'Hopital is working. Okay, next one. Sub a 0 in. Let's go through this. Don't forget direct sub first. Sometimes that works. You don't want to waste your time doing all this work. So you're going to get 1 minus 1, which is 0, minus 0, which is 0, over 0. Good. We did not know what to do with that. Let's L'Hopital this. Okay, so L'Hopital, we are going to get 1/2, 1 plus x to the -1/2. Don't forget the derivative of the inside, it just happens to be 1. The derivative of 1 is gone. Now, if you need to think of this, I don't want you to use quotient rule here. Isn't this the same as -1/2 x? Let's fix that. Okay, so then the derivative of -1/2 x is just a -1/2 all over the derivative of the bottom, which is 2x. This is looking super messy. How about we rewrite it? So 1 over 2 root 1 plus x minus 1/2 over 2x. Now here you really could divide, multiply everything by 2 and get rid of the 2 in the denominator. I'm just going to leave it. I'm not bothered by it, but if you want to, you might see that. Before we go on though, let's go and look at the problem. So we cleaned it up. So we used L'Hopital. Let's make note of that. So we use L'Hopital in the first step. Now we get to this nice cleaned up thing. Let's cross our fingers and hope that it works. However, are you guys seeing 0 in the bottom? And if that's gone, we have a 1/2 minus 1/2, which is 0. So we're going to have to L'Hopital this again. Not surprised based on the directions. Now, remember when you do this, this function and this function were the same, right? All I did in this step right here was rewrite it to get rid of this. But now if I have to take the derivative again, I really want to look here because that's so much more calculus friendly. Let's bring the exponent down and get -1/4. Copy this and decrease this by 1. The derivative of the inside is 1. So we're going to get -1/4, 1 plus x to the -3/2. Finally, some good news. Derivative of a 1/2 is 0. And even better news, we no longer have an x in the bottom because the derivative of 2x is 2. Let's copy this over, cross our fingers that this is going to work. -1/4 goes in the bottom. This 1 plus x also goes in the bottom. It's cubed in the square root. And then we also have a 2 on the bottom. Okay, so if we are to write this out a little better, maybe you guys did it better on the first go round, we have the limit as x goes to 0, and we're going to have -1/8, 1 plus x cubed square root. As x goes to 0, this whole thing inside goes to 1. Whew, I'm glad we did not have to do this again. -1/8, especially because we're almost done. I would have made it under 20. Let's see if we can. X is going to infinity, guys. What does that mean? That means horizontal asymptote. Now, here's one case where I think L'Hopital is not faster. Looking at this, can't we say same? So answer is 3/2. We saw this problem earlier. But let's go ahead and see how it applies. You can use either way. On this one, we get infinity over infinity, which means go ahead and L'Hopital it. And then you get, what, 6x over 4x? What's that? Isn't that still infinity over infinity? Let's L'Hopital it again and get 6 over 4. So just recapping, the derivative of this is 6x, and the derivative of 2x squared plus 1 is 4x. Now we have a constant. There's nothing even to sub x into. This just reduces to 3/2, which is what we got right here. Okay, and again, look at, because we knew that, we didn't even have to use L'Hopital, but hey, if you do, it's good. Okay, so don't forget about the little drama between Bernoulli and L'Hopital. We'll talk about that in class, and I'll see you guys later.